Since we're a pretty small group, feel free to interrupt me anytime because it'll make for a bit of a nicer discussion. So today, I'm going to tell you about what direction my atoms are pointing, and I'm going to tell you what direction my atoms are pointing relative to a whole myriad of different things. Basically, we're very interested in the orientation of particular thulium ions in a particular thulium crystal. Now, that may sound specific, but it connects pretty nicely to some nice physics, so I'll talk about that stuff too. So just as a brief outline, I'll start with a basics of what we're trying to do, entanglement over distance and quantum networking. I'll talk about some of the devices that people are making with some lovely atoms. And then I'll start to get into more specifics about our particular thulium atoms, our particular crystals, and some of the Hamiltonian structure that's behind them. I'll continue by detailing some experiments, both ODNMR and spectral hole burning, that we use to determine some hyperfine tensors of the thulium atoms in a yttrium gallium garnet host. And then I will take us back to some of the applications I mentioned at the beginning and mention how we might be able to use some of these measurements in a more applied context, because we get a bit deep into the material study. So without further ado, I also want to warn you that we live in a pandemic, and unfortunately this talk contains a lot of different axes which rotate relative to one another in 3D space. And unfortunately, I can't be standing in front of you rotating two right-hand ruled hands in front of you to indicate what I'm talking about. So if you're not good at thinking in 3D geometry, please stop me to ask questions or make me go to a slide that has a nice, clear picture. I'm happy to, so that we can keep everyone sort of on board as we talk through these different rotations that are involved. So first things first, quantum networking. Everybody is here because they're probably interested in quantum networking. The name of the game will be distributing entangled states over distance, and this can provide us with some untold benefits that I won't tell you about, but you can read about here. This is one of many reviews, so the benefits and the protocols that we can talk about running range from some classic quantum cryptography all the way to protocols involving voting and distributed quantum computing. So there's really a whole range of options. But to carry out some of these more complex protocols, then we need to start to talk about what devices we might need in a quantum network. And that includes things like lasers to tune and drive all sorts of different atoms. This means single photon light, powerful light. It means quantum memories, maybe some very accurate clocks, and maybe quantum computers themselves if they become part of the network one day. So really, there's a lot of work to be done, and work to be done at all levels, studying the materials that make up these devices, the devices themselves, how to optimize them, and then how to use the devices on a larger scale in one of these networks, running protocols or programs of some sort. I will also say that there's really not much we're going to do that doesn't involve atoms. So I think I've mentioned so far that light will be center stage in a lot of these devices and protocols that we hope to run, but so will atoms. And I will be spending the talk focusing in on a specific set of parameters about a specific set of atoms that lie within this lovely periodic table. To start that narrowing process, I want to say that I work specifically with rare earth ions, which are this top green row of the periodic table, and more specifically with thulium number 69. But some of the physics that I'm here to tell you about today does apply beyond just this atom. And I hope that I can connect it pretty well to some other parameters that are around and other materials. So we'll glance past maybe some cesium, some rubidium, some strontium along the way and just sort of say, we have a nice connection, even though we're seeing the physics on a platform based on thulium as well. So I want to kick things off by talking a little bit about an atomic clock. Here is a cesium resonator in the Nature paper from 1955 that sort of kicked it off as a frequency reference. And I'll read a quick passage from it. The frequency of the central line of the Zeeman pattern is, however, to first order, independent of the value of the field given by some expression, where h is the field in Oersted's, some old unit of magnetic field, and v naught, which is approximately some number of counts per second, a fundamental constant of the atom. So these guys who designed an atomic clock from cesium took a specific transition in their specific ion and measured it to very high accuracy and realized that despite the field they applied, despite the variance in some external parameter, that this constant remained and that it was something they could use to their advantage, and that it remained robust, not just to intentional changes of a magnetic field around their cesium atoms, but that also unintentional changes did not seem to perturb this constant frequency, and they used it to their advantage. Now, this is a theme that I'm going to introduce a bit now, but come back to sort of more at the end. It's the idea of a clock transition. So transitions on many different energy scales within the atoms I discussed before. Sorry, just one sec. Transitions on many different energy scales can be clock transitions, ones that are invariant when you apply a series of different fields to your atom. So it may be two levels that don't tend to move relative to one another as you apply a magnetic field. It could be two optical levels, spin levels, and these transitions can be used in a number of different ways. So people make lasers out of them, people make clocks out of them, people investigate materials that have a number of different clock transitions, and also long-lived quantum memories. So the physics behind this, creating a transition which acts sort of similarly to this cesium idea, no change with change to your magnetic field, is a bit of an important physical idea that crops up throughout a number of different fields and throughout maybe many of the devices that may make up one of these quantum networks. Just as a pair of examples to highlight this, here's a couple of results. One from an ion trap you see on the bottom, and one from a rare earth ion doped crystal here on the top. And here you can see these two people found a way to isolate their quantum system, whether it was the state of an ion trapped quantum computer, quantum memory, or the state of praseodymium atoms, which would also store light. And they found a way to isolate them from noise, either noise that they introduced in the case of the ion trap and some beryllium atoms, or noise that was just present due to the surrounding host crystal in the case of praseodymium. Now, for these quantum systems, they're interested in preserving the coherence of their system as long as possible. And you can see that by these long curves at the special points, at these accessing the clock transitions. But you can also see this buys them maybe orders of magnitude in each case in terms of how long their coherence will last. So finding these decoherence-free subspaces, or places where variation among your magnetic field or other effects that may cause noise, in the case of the ion trap, it's AC electric fields, finding these invariant transitions, despite noise, are quite powerful and have already led to devices that improve a lot. So keep that in mind. Now, to do so, they really need a detailed understanding of the energy level structure that they're working with, of the level schemes that they're doing all of their operations with. And this is given by the Hamiltonian of the system. So you can imagine very good understanding of a Hamiltonian of a given system translates to being able to build a device in the first place, but it's also how you use those systems. So if you can take your system that already works, say a praseodymium crystal, and find a new way to use it such that the coherence time is much longer, you might want to think about designing your device that way. Same for ion traps. So one thing we're going to keep an eye out for is variance in transition energy between whatever defines your ground and excited states, between either a pair of spin levels or optical levels or other levels that are present within your device that you're trying to create, and making sure that those levels don't change frequency with respect to one another over time. Now, if you're relying on a scheme that includes some sort of controlled de or rephasing, then you can see that that energy change will cause fewer of your dipoles to de or rephase at the correct time. But it also can link back to Heisenberg uncertainty, where a certain amount of change in frequency results in a certain amount of uncertainty in time as well. So we're really going to look for times when we can guarantee that the energy difference between a pair of levels, our interested pair of levels, remains constant. Okay, so keep an eye on this throughout in the back of your mind. And now let's dive into some of the actual levels that we're working with. So for a more general case of some thulium, of some rare earth ion in some host crystal with some symmetry, we can use this general Hamiltonian, a free ion term plus a crystal field term plus a nuclear quadrupole term plus a hyperfine term plus an electronic Zeeman term plus a nuclear Zeeman term really makes for a handful of things to consider, but quickly we can pare this down. So in terms of the first two, these are our largest, orders of magnitude above the others. And so if we're very careful in the frequency of the laser or the frequency that we're using to address these ions, we know exactly which free ion and crystal field levels we're addressing at all times. And this is not really something we need to take into consideration when we're trying to understand all of this, all of the shifts that are present in this Hamiltonian. Now, also lucky for us, thulium has a nuclear spin of 1/2. So the nuclear quadrupole term goes to 0 as well, which leaves us sort of 3 more magnetic dependent terms at the end, the hyperfine term, electronic Zeeman term, and nuclear Zeeman term that are left. Now, some smart guy named Teplov expanded these using perturbation theory to second order and was able to sort of redefine these terms in the form of an enhanced Zeeman interaction and a quadratic Zeeman interaction that are shown here. Now, this is in terms of a lot of atomic constants, which are well known for thulium because they've been studied via NMR and atomic beams. So in terms of this Hamiltonian, likely there's not very many unknowns. The main one being just this lambda. So what is lambda? Lambda holds all of our directional information for these atoms. Now you might wonder, why does a Zeeman term, sort of this enhanced Zeeman term, these first two, have directional information if it's just B dot I, your nuclear spin, your nuclear spin interacting with your external magnetic field? Well, it's because it's not exactly a Zeeman interaction. It's an enhanced Zeeman interaction, one where the spin of the nucleus creates a net magnetization of the electron orbitals. And these orbitals and that nuclear spin then interact with some external field. This actually does have some orientation to it that is defined by this lambda tensor. Now, likewise, the third remaining quadratic Zeeman term also contains that same lambda tensor and has some directional information involved because it's the second order electronic Zeeman term. So in terms of unknowns, things we need to still classify are, say, 18 entries of this lambda tensor, a 3x3 tensor for both our ground and excited states that we're interested in creating a device with. Now we can get a bit more specific and say, okay, YGG is a garnet, so we know its crystal symmetry, and this will allow us to simplify things a bit further. So YGG is a cubic crystal. It has an O10H space group symmetry. And for the sites where thulium substitutes yttrium, it has a D2 point symmetry. So in these sites specifically, we can diagonalize the lambda tensor and wind up with fewer unknowns because of it. If we do this, we go from, say, 18 unknowns down to 3 per level, where we can treat it just like a regular dot product. between the G, X, Y, and Z terms of this lambda tensor that hold all of the orientation information as long as we're referring to the correct sites at the correct times. Now, this has been shown very clearly for other garnet crystals, but for YGG, it's a bit of an assumption. So when we come out with results later on, maybe it will show us that our assumption was correct and that we do actually understand the shape, structure, and symmetry that are present in garnet crystals. Sorry, yttrium gallium garnet crystals. Now I'll make one more assumption, and that is that thulium ions in all sites are in magnetically equivalent environments. And if you want to ask about the details of this, that's actually not such a clear definition sometimes. So we can get into that a bit later, but for now, let's consider an example on the simplest of terms before we look at a real garnet structure. So if I consider two thulium sites, so thulium site 1 and thulium site 2, then each will have some local axes that I'm going to tell you about in a minute. But if the local axes for thulium site 1 are defined by the big blue arrows on the left and the site 2 axes are defined by the big blue arrows on the right, and I apply some field, some magnetic field with my big magnetic field red arrow, then I would say for site 1, my magnetic field projects on the y-axis alone. And for site 2, my magnetic field projects on the negative x-axis. Maybe we'll forget our negative signs in a bit. Now, switching things up, I can change the direction of a magnetic field and change the projection on both sites, where now I project on the x-axis of site 1 and the y-axis of site 2. Okay, things have been maybe clear so far. What about in between? So if I consider a projection halfway between site 1, y, and x, then I project on both. I essentially project on the y plus x axis of site 1, and I project on the y plus x axis of site 2 as well, within some negative signs. Now, maybe this drives home the point that though my orientation of site 1 and site 2's local frame is different, there exists some projections such that they will act the same, such that they both share the same projection of magnetic field on their own local axes. Now, this is in the simplest case. Now let's move to the case of yttrium gallium garnet. So for this, there are lots of different directions flying around, and I'll describe each of them now. But you can imagine then that we have to talk about these projections on each of 6 thulium sites shown here by, I think I'm calling them cuboids, in the 6 different colors. So we expect there to be 6 thulium sites: black, purple, yellow, orange, blue, and green. And we expect them to be oriented this way with respect to a few different sets of axes. The first one I want to point out is the cubic crystal axes. I said yttrium gallium garnet was a cubic crystal, and the black large axes here denote sort of the orientation of the cube that defines the crystal. Now, within this crystal, there's also just another set of 3 orthogonal crystal axes that are a bit useful to know about. Those are the red large axes. And these I like to call the symmetric axes because they cast the thulium sites into some of the same electromagnetic environments. So you can imagine if you project a field along, say, the 001 axis or the 100 axis, you're maybe not projecting so similarly on many of these different sites. If you do project along some of the red axes, you do wind up projecting very similarly on larger subsets of the thulium sites that we're interested in. Okay, then lastly, I also want to point out this local XYZ shown here in black. So for the site that's also in black, these are the local site axes. So for each of the 6 sites, there is a frame with an XYZ axis defined at similar orientation to the cuboid, such that we understand the orientation of each ion with respect to the total crystal cell. This means that if I give you a direction, any direction, relative to a cubic crystal axis or relative to one of these red symmetric axes, then I can also tell you the projection of that particular direction on each of the 6 thulium ions' local axes. And this is going to be an important point that we track throughout the rest of these experiments. Okay, so we maybe have a handle on where everything is pointing. I am 20 minutes in and I've already fulfilled my talk title. Which direction are my atoms pointing? This is the direction that my atoms are pointing, relative to some crystal cell walls. But maybe it's not the most interesting of directions to know about. So let's delve a little further and try and unearth some more interesting directions. Now, to do that, let's go into the details specifically of thulium in the yttrium gallium garnet ion host. So rare earth ion doped crystals are a broad field. They're studied by a number of groups across the world, and they involve large ensembles of ions doped into generally yttrium-based crystals. Now, instead of working with, say, a trapped ion, where you have just a single atom floating in free space with its single transition energy, instead we're working with this huge ensemble, and where each ion occupies a slightly different environment within the crystal. Now, each ion has its own transition between levels, say the 3H6 to 3H4 transition, but this transition energy can vary from ion to ion across the ensemble, creating a huge inhomogeneous broadening, which you can see shown in a picture here on the left. Now, this inhomogeneous broadening is the same transition across many ions, but slightly shifted from one another by different local crystalline environments. Now, considering this at 0 magnetic field, we only have these 2 levels. But we can start to split them by applying magnetic fields and getting the splittings that we'd predict from Zeeman terms and the Hamiltonian I showed you earlier. And a lot of the rest of this talk is going to be about classifying these 2 splittings, delta G and delta E, as we apply magnetic fields at different orientations and different magnitudes. Now, one way we really use to characterize rare earth ions in an inhomogeneously broadened absorption line in one of these rare earth ion doped crystals is via spectral hole burning. So I'll just walk through a couple of the details of this experiment, and then they will come up again later because it was really a workhorse for us in gathering these results. With spectral hole burning, we create a hole in that inhomogeneously broadened absorption profile. So we had our 3H6 to 3H4 transition, and that absorbs light. But when we shine light on a particular frequency within that inhomogeneous profile, we drive population through the different levels that are available. Now, if we have a laser that drives on the blue transition, atoms are pumped out of the ground state and thus cannot absorb at that frequency, and they create some transparency or transmission on that particular frequency. And when they do that, they create a main spectral hole due to the absence of population in this level. Now, that population can rest either in this excited level or in another created spin level. But in either case, it's not here to absorb light. Now, if it does wind up in that other spin level, it creates a small pile, I would say, of population at that frequency. And if we control this splitting, this delta G, between the 2 ground state spin levels, then we know this energy difference to some degree. We create it and we can observe it by looking at that small buildup of population, or what I'm going to call an antihole. Now, for every main hole, there's symmetric antiholes on either side due to the inhomogeneous broadening. But there's also a host of other features that occur when you start to consider more transitions throughout this sort of 4-level structure. So I'd say at the end of the day, probably we expect a whole lot of features from a single thulium atom in a magnetic field in a rare earth ion doped crystal. We expect features, both antiholes here and side holes that I will talk through a bit later at plus minus the splitting delta G, plus minus the splitting delta G plus delta E, and plus minus the splitting delta G minus the splitting delta E. And these features indicate which of these levels holds the most population. And we can see this by keeping an eye on the transmission or the transparency of the rare earth isotope sample at each of these frequencies. Okay, let's add another layer.
Jake?
Yeah.
May I interrupt you?
Sure.
So could you please repeat the process for anti-holes? I'm not sure that I got it.
Sure.
How did you?
So this slide or the next one?
Yeah, this one.
So when I drive on the particular blue frequency, I create a transparency because I remove population from this ground state. Now that population is driven into this excited state, but from there it can decay, and it will decay spontaneously, given by the lifetime of this level, which in our material is something like a millisecond. Now when it decays, it has two places of lower energy that it can drop back down to. It could be the original spin level, where it came from originally, or it could be the other spin level. Now, if it's the original spin level, there is likely still a pump laser resonant with that ion, and so it gets re-excited. But if it happens to be the other spin level, and this happens with some probability given by the branching ratio, if it happens to be the other spin level, that spin level and that transition is then out of resonance with your driving laser. And so the population can be left there to build up. And the way we see this is a change in the absorption, not of the blue frequency, but of the orange frequency, which relative to the blue frequency is 1 delta G away in frequency space. Does that answer your question?
Yeah, thanks.
Excellent. Okay, so adding ODNMR. Actually, that was a perfect time for the question because it made me really walk through where my atomic population is during this process. Now, like I say, the transparency indicates an imbalance of population between the two ground state spin levels, just like the anti-hole does. And that imbalance is something we watch by keeping an eye on a spectral hole. Now, we can attempt to change this balance by optical pumping, but we can also change it by other means. Namely by using an RF field to drive in between these two levels indicated by the red arrow. Now, this energy is much, much smaller. It's not an optical frequency. It's something like some number of megahertz or gigahertz. And that's entirely determined by how much magnetic field we apply to create this delta G splitting. Now, if we have an imbalanced population, and we apply some RF field, then as we drive coherently, sooner or later, we'll wind up with balanced population between the two levels again. And this will result in no spectral hole and no anti-hole features. So if we're watching our spectral hole, we can tell when we are driving with our RF field on resonance with this transition. Now, this is something we're very interested in. We want to determine delta G for a whole series of fields and for a whole series of orientations. And so if we apply many different RF fields to our sample, we can check which ones get rid of our spectral hole, rebalance our population, and destroy our transmission through the sample. And we do just that to conduct ODNMR. So here's a...
Sorry, this is probably a pretty simple question, but if you're driving it at coherently at that transition, why don't they all end up in the higher ground level? Like, why aren't they all excited to the higher ground level? Why do they balance?
We end up re-equalizing the population between the two levels because you can't coherently drive forever. There is some decay from one level to another.
What do you mean by coherently drive then?
With a frequency that matches the level splitting, we I mean, I think that is coherent driving.
There's a damped harmonic oscillator, sort of like
yeah.
you end up with a balanced population. We will always end up with a 50-50 split, even if you're driving Rabi oscillations, right?
Yeah,
Rabi
exactly.
are 50% of the time in the excited state and 50% of the time in the ground state. So it's always going to be half-half. If they're coherently driven, then they keep going up and down. If there's damping, then you damp out the oscillations because of spontaneous emission. You know, one atom spontaneously emits, then it keeps sort of starting on its Rabi oscillation, but now on its own phase compared to all the others. And slowly, then they'll add up, driving Rabi oscillations, but all incoherently, which means just like a flat line in the middle.
Yeah,
Kim, not convinced.
exactly.
Are you?
Hopefully that answers the question.
I don't think I get it, but I'm not, this isn't my field.
Okay, we can talk more maybe at the end.
Sure.
So to give you maybe more of a physical intuition of how we do this, we take our rare earth ion crystal slab and we put it in a tiny holder like this one, and we insert that holder into a coil as shown here in this small mount. And the mount has some gearing so that we can rotate it over a series of different fields, a series of different field orientations. Now we take this whole mount and we lower it into a cryostat as shown in some of these pictures just here. But even when it's down in there, you can see it's in a coil that provides an external magnetic field, and we still have optical access. So there's a number of different ways we're addressing this crystal. But throughout this process, we're burning a spectral hole. We're watching its depth and the amount of transmission we have as we vary a driving RF field through this coil. And as we do that, we see changes to the height in the spectral hole over a series of different frequencies. So here are a couple resonances that we see that occur for just some random angle and some random spectral hole in this material. Now, just to generate a scan like this one requires optimization over a pretty large parameter space. We're making sure we have population in the correct levels so that we can drive it. We're making sure that all our samples are at the correct temperature and that we have the correct laser power, creating a spectral hole, and the correct RF power so that we can see the change in the population of that spectral hole. And we think we do a few tests to make sure that these are indeed the resonances we're looking for. The first one is we scan over a much broader range than 4 megahertz just to start. And we're able to see that all the resonances are mainly contained below 4 megahertz, about where we'd expect them for these materials. Secondly, we verify that these spectral features disappear when we turn off our magnetic field, and also that they increase linearly as we increase our magnetic field. So these are all good signs that we have the features we're looking for in these sorts of resonance scans. Now, once we can generate a spectra like this at some angle and some magnitude, the next step is to generate them at a whole series of angles and a whole series of magnitudes so that we can get a handle on that orientational information we're looking for. Now, that ends up turning out a huge scatter plot like this, where you have many ODNMR resonances at many different frequencies for each angle. And I have a little diagram here indicating the series of angles over which we rotated relative to the crystal axes. So you can imagine for each column here, we know exactly the projection on all 6 thulium sites. And so we can make a bit of a guess at what the G-tensor might be for the thulium ions to give us these resonances at a series of different angles. Now, when we do that, you break down your big data set into something site by site, you actually see pretty decent agreement between many of the different site curves that allows us to guess a G-tensor that maybe makes sense and explains all the resonances we see. Now, there is still some variance to the data, so we verify by rotating the crystal to a different orientation and repeat. Oh, here's the whole thing put together again with some values. So our G values in splittings and our fit confidence for this one direction. We do this whole thing by rotating again, and again we get decent agreement for another tensor. And luckily at the end, these tensors match quite closely with one another. That gives us more confidence that these are indeed the G-tensor values that we're interested in. Now, that's great, but it is just 3 values that represent this, the ground state tensor. So it's time to turn to the excited state tensor values, and we have to figure out, not just from ODNMR, but from spectral hole burning as well, what those might be. So in this case, ODNMR is a bit harder to carry out in the excited state because it's a tough balance of making sure your population remains in the excited state as you drive with an RF field. And in this case, we couldn't get it to work. So we turned to spectral hole burning with hopes that we could derive the information we needed. Now, I said I'd come back to this. You'll notice a few of the other spectral features occur at splittings of delta G plus delta E, delta G minus delta E. And in fact, the one that occurs closest to the main hole is this guy, this one that occurs at delta G minus delta E. And this was the one that we thought we could see in a scan like this one. So actually, observing all of the spectral features is a bit difficult for a given hole spectra. So when we look at one such as this, we imagine, okay, if we don't see everything, which ones do we see? Well, likely the one that's closest to our center spectral hole, that G minus E antihole. And if we know we always have the G minus E antihole, then from known delta G splittings, we can derive the delta E splittings that accompany it to produce these antiholes at a series of different rotations. So we did just this, and we rotate again, looking at the spectral locations of those antiholes across a series of different fields and resonances, and come up with a tensor value that matches it, hopefully pretty well. And again, we flip to another orientation that again maybe matches it pretty well and matches the first one, such that we have some confidence in what the values are at the end. Now, these values are the 6 unknowns we were looking for in our Hamiltonian from the start. And they will inform us of some interesting things going forward now that there are no remaining unknowns in the spin Hamiltonian. So we know the energy levels. We know we get a splitting of each state. We know how those energy levels tend to move. And we want to use this information to optimize a few different devices. So one of them is AFC quantum memories. And then maybe I'll hark back to some of my discussion about clocks and decoherence in the very beginning related to these tensor values. So for AFC quantum memories, one thing that is very important is the splitting of these spectral features in the material you're using to create a memory. Now, AFC is an atomic frequency comb, and that's an example of one, burnt in thulium YAG here on the right. And you can see we shape the inhomogeneous broadening of that absorption profile for the rare earth ion doped crystal into a comb-like feature. And when you do this, and then you shine light resonant with this comb structure, you get out sometime later, after the absorption of that light, an echo. So you have some input pulse, and sometime later you get an echo pulse re-emitted. And the amount of time that pulse is stored for as a quantum memory and the efficiency of that re-emission are given by the parameters of the comb that you can shape in the inhomogeneously broadened absorption profile. Now, the combs that we can shape, we would love to be arbitrary, but unfortunately they're not. I just told you a number of slides ago here that when I burn a spectral hole, I get a number of separate features. So when I burn spectral holes to create an AFC, I get a number of spectral features near each of these holes that I need to account for and make sure that they participate in the comb structure in the proper way. So one way I do this is by knowing exactly what my splitting will be for a particular angle and optimizing that value so that I can create a perfect AFC as I want. So we can translate a lot of these tensor values into exactly the splittings we're interested in for an AFC to get desired storage times and desired efficiencies. Now I think probably I'm going to be running short on time in a few minutes, so I'm going to keep going. And if we have more questions about that, we can talk about that in a minute. One thing that's very important about these quantum memories is that storage time. And it is ultimately limited by the coherence time of the transition we're interested in. So one thing that was very important to the ion trappers and the people with Praecidemium early on was extending this coherence time such that they could extend the storage time of their quantum memories. We also will look to extend the storage time of our quantum memories. And to do this, we're going to use a similar scheme. We're going to use something called an optical clock transition. And so let's start heading in that direction to get a feel for things. Now, the Hamiltonian I showed you at the beginning had some unknowns, but now that we know them, I'm going to call the different constants you saw just some constant, alpha and gamma. And if I look then at the Hamiltonian of a single spin level in either the ground or excited state, it's a quadratic function that looks like this, where these constants are given and variable by the tensors we measured, but where it has some quadratic shape with a maximum, where it's the sum of a linear term and a quadratic term. Now, one thing I know about this is that it will have an extrema. It must have an extrema, and for one of the two spin states, that extrema must be at some positive field magnitude. So you can kind of imagine it becomes the interplay between the quadratic term, which lowers the energy, and the linear term, which increases the energy of one of the spin states, for example. So you can kind of see at some point you get a trade-off between those two terms that results in an extrema or a maximum of that level energy. Now, switching from talking about sort of a general picture and a levels specific energy to a more specific picture and a transition energy instead, so the difference between the energy levels. Instead, we get a picture that looks like this. Considering the blue and the orange transitions now, if we look at the energy over a series of different fields, we can see that that maxima or that extrema still exists. Now, that means if I take a partial derivative, that the change in this transition frequency with respect to increasing field magnitude goes to 0 at this point, at this field magnitude. And this is one of the beginning prerequisites for having a clock transition between these two different states. Now, it's not the only prerequisite, but it is interesting to see that if we can get these other two derivatives to go to 0 as well, then we may have the makings of a full optical clock transition in this material, which in turn may yield the coherence improvements that have been seen in other materials. So one thing I did was map out using the tensors. Again, I say these constants that describe this parabola vary with orientation based on the tensors that we measured, was map out the field value at which this extrema occurs and at which this first condition of an optical clock transition is met for one spin state at a whole series of different angles. So at a whole series of different angles, you can see there's lots of angles for which there is no positive field you can apply that creates an extrema in your energy change. But there are a number of angles for which you do meet this first condition of an optical clock transition. Now, let's worry about the other two gradients. I also look for a particular, once I look at a particular point, I know the field for that particular orientation for which the energy, the transition energy, should be invariant with increasing field magnitude. So for every point, I can consider the angular change of the transition energy at that specific field magnitude. And I can also consider the gradient of the angular change at that specific field magnitude. And I do that in this figure, considering these two angular gradients can also now be set to 0 if you go to a specific point. Here, there are two, one for each of the two spin states, one here at 19 millitesla, 55 degrees theta from the crystal cubic cell, and minus 15 degrees phi from the crystal cubic cell, which sets all three of these terms to 0. Now, this has the makings of a full optical clock transition, one where the transition energy between your spin down ground state and your spin down excited state does not change as you vary, either on purpose or due to noise in your crystal environment, the magnetic field around your ions. And this is of particular interest.
Jake,
Now,
Jake,
yeah.
it says on the axis gradient magnitude. What do you mean by gradient magnitude?
Gradient magnitude. So I mapped out the angular change to the transition frequency, and then I took the gradient of it. So low gradient is 0. That's good. High gradient is
oh, hang on.
not
So
good.
it's inverted scale here. So 0 is white,
Yeah.
and is somewhere so out of scale or something like that almost.
Yeah, and so
Oh.
there are finite values on everything here because I did not have infinite precision for some of the calculations.
Right.
But the gradient does go to 0. There are a few extremas here,
Yeah.
which means you have a sort of a maximum of a surface.
Yeah. No, the inverted scale threw me. I mean, the fact that.
Yeah, no problem.
Thank you.
So you have sort of an extrema of a surface here between the two angles, where you can also send these transition energy gradients to 0. Now, this is all analysis done for a single site, but we can apply this same logic to all of the sites. And relative to the crystal axes, we get a whole list of potential optical clock transitions in this material for each of the different sites. Now, that's great. But the story doesn't just end there. We need to try and decide which of these shows the potential for greatest improvement of the coherence times. And we also need to come up with an idea for how we might actually address them, because addressing a single site in this material and even a single spin transition in this material is quite difficult. So it's promising, but it's maybe not the final answer for improving the coherence. To get some more physical intuition about what that means, just shown on the left is the optical transition frequency. So I can show you the exact movement of each of the energy levels I'm talking about. And I only show in one direction here, but the other two directions are implied from above. The tangent line to these curves are parallel to one another at this one specific field point. So we do have the invariance here as we change the field magnitude in both directions, and as we change the angular, as we change the angle of the applied magnetic field in this case as well. Now, back to my trusty crystal diagram. These directions, just shown from the table before, here are a few of them, are physical directions within your crystal. And I would say they are some of the most interesting in thulium gallium garnet going forward, because these may be the ones that lead to improved optical coherence. And this sort of sums up where I would want my magnetic field pointing, given that I know where my thulium atoms are pointing from the tensors before. So like I say, the atoms will probably lead the way in making these nice devices. So if we continue some of these material studies, hopefully we can track the improvements from understanding of the material through to device improvements through to exciting procedures and protocols for quantum networking. Hopefully, looking at an example material like thulium YGG tells you a bit about ODNMR, spectral hole burning, AFC creation, and even clock transitions. And these clock transitions are extremely powerful tools used throughout a lot of different areas of physics. So grab connections to them when you can. With that, I'd like to thank all the collaborators for this and co-authors as well, because couldn't have done it without them. Okay, and that's what I have for you. Thanks, everyone.
Sorry, I was muted. Thanks, Jake. That was a really good talk. I think we definitely learned a lot. So I'll turn off the recording now so that people can freely ask questions. So you're welcome to